Assalamualaikum warahmatullahi wabarakatuh and good morning. Okay. We continue our advanced geotechnics class. Okay. From our previous discussions, okay, we already discussed on the several soil mechanics example and also definitions. Okay. So I have already covered on the explanation of the active, passive, and at rest. Okay. So then I start first with the earth pressure at rest. Okay. And then show one example, okay, on the calculations for earth pressure at rest. Okay. So for today we will continue on the active and passive. Okay. So for the active and passive, okay, the first we start with the without having any or do we assume what we call the wall is smooth. Okay. So later on we will discuss on what will happen if we have what we call as a rough and also angle. They call as a, they use the term of better angle, where the what we call as the retaining wall, okay, is not 90 degree. Okay, so let's say it has some angle, okay, and there will be a discussion, okay, on the backfill, okay, where there has a slope. Okay. Okay. So the derivations on that part is very a little bit difficult. Okay. So we only go a little bit on the simplifications of the equation. Okay. And I will try to provide what we call as the derivation before our next class. Okay. So this is for smooth and without having, they call it a better angle, okay? And without the backfill is flat. Okay? So yeah, this is for the derivation. If you look on the page number 1, okay? So this is to explain how the derivation process, okay, for this page 42. Okay. Okay, so you can go to, okay, on how the derivation work. Okay. This is for the active. Okay. Okay. And this is for the passive. Okay. And this is for the undrained cohesive type of material. Okay. So this is the more circle, okay, for the zone number 1, okay, where sigma 1 is the major and sigma 3 is the minor. And the direction of sigma 1 is vertical and the direction of the sigma 3 is horizontal. Okay. And for the passive, okay, so since the movement of the wall towards the passive, so then the sigma 1 is the major and it is in horizontal direction, while sigma 3 is the minor and it is in vertical directions. Okay. So this is sigma 3 and sigma 1. Okay. So later on, when we want to get what is the active earth pressure, okay, the value, the equation is sigma V, which is the vertical, which is the effective vertical stress, okay, multiply with the depth, okay, and minus 2 Cu. Okay. While for the passive, okay, the the there is a changes of the definition of sigma 1, because sigma 1 will represent by the sigma h, and sigma 3 is represented by what we call as sigma 3, okay, sigma b. Okay. So then the equation is written as sigma v times z plus 2cu. Okay, so you can look on this derivation. Okay. Okay, this is for the drain concealers material. Okay, so I explain on this derivation, how it works. Okay, so based on the sign, okay, because if there is a cohesiveness material, so there is a internal friction angle, which is the phi. Okay. So the phi is contributes from the roughness of the particles, okay, in cohesiveness material. Okay. So then we want to get what is the ratio, or what is the ratio between T and S1. Okay. So T is this what we call the opposite of the theta, or of the phi. Okay. And S1 is the hypotenuse. Okay. So if we look on this one, okay, sigma 1 minus sigma 3 is the T, okay, over sigma 1 plus sigma 3. Okay. In order to get this equation, so then we need to understand first what is the T. Okay. So I have put in this explanation. Alright. Okay, how to get the T? Okay. So T S1, okay. So S1 is the distance, okay, between 0, for example here, to sigma 3, then plus T. Okay. So later on, what we call as the ratio between the sigma H over sigma V is considered as what we call as the coefficient of active pressure, okay, Ka. So this is the equations for active earth pressure. Okay. So these equations, okay, will be expanded based on what we call as the situations. Okay? If we consider for the problem that has a better angle, okay, and also the wall is rough and there is a sloping on the top of the backfill. Okay. So then for the next discussion, okay, the KA has a different derivations. Okay. Okay, so that is for the KA. Okay, then this is for the passive. Okay, the previous one is for the active. Okay, so the passive is KP equal 1 plus sine phi over 1 minus sine phi. Okay, while this is for the general phi and C material. Okay. So now we look on how the derivation works. Okay. So if there is a phi and C, okay, so the more circle will be we'll have what we have a C value, okay, and then also a phi. Okay. Then if we extend the line, okay, so then there will be an additional what we call as a C cot phi. Okay. So from here, okay, we try to simplify, okay, the equations, okay, to get what will be the full equations to determine the active or passive lateral force. Okay. So look on the derivation for passive. Okay. So how I obtain, okay, what we call the 11.9 equation, okay, where actually the initial equations is T over S. Okay. So we imagine this is T and this is S, the distance from this point to the center of the thermal column. Okay. So this is the T and this is the S. C cot phi plus sigma 3 plus sigma 1 minus sigma 3. Okay. So after we put the equations, which is the ratio between T over S, so then we simplified it into this equation, which is similar with the equation of 11.9. Okay. So then to get what is the sigma 3, okay, so then we do some rearrangements. Okay. We do some rearrangements. Okay. Where some need to move to the right, okay, and remain on the left, and move to the left and remain on the right. Okay. So then this is how the derivation work. For example, cot, okay, is 1 over tangent. Okay. So then we can simplify it into cos. Okay, because sine over tangent is a cos. Okay, so this is cot 1 over tangent. So sine over tangent is cos. Okay. Okay, so how they obtain the cos here? Okay, from the cot. Okay. then we just simplified it, okay, until we obtain, okay, and then we need to use what we call as a trigonometry identity. Okay. So it's very time consuming, okay, when we want to derive or want to explain how the equation works. Okay, okay. That's why I could not derive all at the moment. Okay. But later on, I will work on it and share with you. Okay. Because when we go for a very complicated problems, so it demands us to understand more on the mathematical uh, knowledge or understanding. Okay, then this is the what we call as the uh, trigonometry identity. Okay. So I work on this trigonometry identity. Okay. You can go in detail later on. So how the process works. Okay. All right. And then simplify it into same equations with this sigma 3 equations. Okay. So means that I have what we call as a proof that, okay, from sigma phi in the 11.9 is similar with the sigma 3. Okay. Okay. Okay, perhaps in your test, here I will give a very simple on how to prove the equation. Okay. If I give you this example, okay, so it requires a lot of time for you to spend. Okay, so now we look on the next derivations, okay, on how to prove that tangent square times 45 minus phi over 2 equal to 1 sine phi over 1 sine 1 plus sine phi. Okay. Okay, before we move to this part of the derivation, okay, so we look on this diagram. Okay. So let's say this is what we call as active. Okay, so this is an active. Let me check. This is an active. Okay, active soil conditions. Okay, where the theta, okay, obtained, okay, from this 45 provide a 45 plus p over 2. Okay, so how this angle derived? Okay. So we look on the what we call on this explanation. Okay. Okay, this is for the active. But this is for the passive. Okay. So they use a beta method, okay, to explain, okay, how what we call as the 45 plus phi over 2, okay, for the active, and 45 minus phi over 2. Okay. So basically, okay, the shape of the what we call as of the this angle, okay, is considered as theta. Okay. For the active Rankine state, okay, so the theta is equal to 45 plus phi over 2, okay. Okay, so the beta is equal to 90 minus phi, okay. So when we put in the more, what we call in the more circle, okay, so the what we call is the rotations, okay, is equal to 2 theta, okay. So when we this is a 90 degree, okay. So beta, sorry, okay, beta is because the combination of this triangle and triangular angle, okay, is 180, okay. So it means that if this is 90, okay, and then minus with the E, is equal to the beta, okay. So then for the active for uh, the this part, okay, is equivalent to 2 theta, okay. So from there, okay, what happened in the more circle, okay, when we put in the reality, okay, we need to divide it into half, okay. So for example, if this is 2 theta, okay, so when we want to consider in the reality, okay, so then we need to divide it into 2. So then it represents the theta. Okay. So from here, when we put in the reality conditions, okay, so the theta become 90 over 2 minus or plus phi over 2. Okay. So for the passive, 45 plus P over 2. Okay, while for the, for the active, 45 plus P over 2. And then for the active, for the passive is 45 minus P over 2. Okay, so that is how the 45 plus or minus P over 2 is gain. Okay. Okay. So means that either we can determine the KA based on these equations, or we also can use KA equal to this equation as well. Okay. Okay. So this is how the value come. Okay. To represent for the 45 plus or 45 minus P over 2. Okay. Okay, then in this explanations, okay, I just want to prove, okay, the tangent square 45 minus phi over 2 is equal to 1 minus sine phi over 1 plus sine phi. Okay, so this is how the equation works, how the solution, how the derivation works. Okay, okay, so uh, okay, you can go in detail later on. Okay. So it's very, what we call very long, okay, the derivations. So until I have proved that, okay, what we call as the tangent square, 45 over phi over 2 is equal to 1 minus sine phi over 1 plus sine phi. Okay. Okay. So means that if this is the KA, so we also can use this KA. Okay? Or we can use this equation to get the KA. Okay. Okay, so that is for the derivations for the tangent square 45 minus uh, negative phi over 2 equals to the 1 minus sine phi over 1 plus sine phi. Okay, so it means that for the C and phi, okay, so this is the equation that we will use, okay, to determine what we call as the active and passive. Okay. Now we look for the first example. Okay. Okay. Let me share first the solutions. Okay, for this example. Stop first. Okay, Afiza. Okay, Afiza dah masuk. Can we take a photo first? Okay, can we take a photo first? Gavin. Gavin, can you switch on your camera? Okay. So, okay. So, okay. 1, 2, 3. Alright. Okay. So, let me share first with Dr. Bayang. Okay. I share first. Okay. Look on the the file, the new file that I have shared. Okay. You look on the example. So this is the page number 8. Okay? Is the explanations on the 45 minus phi over 2. Okay? So soreness, okay, at the back of wall considered as an active ranking state. Soreness at in front of the wall considered as the passive ranking state. Right, okay, so then this is the example number 11.1. Okay. So, okay, similar like this one. Okay. So, in this case, okay, um, we use what we call as uh, the the we assume that what we call as the wall is smooth, the friction between wall and saw is smooth, okay? And then there is no better angle on the wall, and also no sloping on the backfill. Okay? So the saw condition adjacent to a sheet pile wall are given in figure 1. Okay? A surcharge pressure of 50 kPa being carried on the surface behind the wall. for soil number 1, you see this is soil number 1, a sand above the water table, okay, EC equal to 0, phi equal to 38, and gamma equal to 18. For soil number 2, a saturated clay, C 10, phi 28, saturated unit weight 20. Plot the distribution of active pressure behind the wall and passive pressure in front of the wall. Okay. So then the thickness of the first soil is 6 meter. The thickness of the second soil is 3 meter. Okay. So then for the active, which is the soil in front of the wall, the thickness is 1.5 meter, and the thickness for the soil number 2 is 3 meter. Okay. Okay, the first step is to determine what we call as the coefficients of active and coefficients of passive. Okay, so either we use the equation 1 sine phi, 1 minus sine phi over 1 plus sine phi, or we can use the tangent square 45 minus phi over 2. Okay, so let's see if you want to use the 45 minus phi over 2. So then try to calculate, okay, tangent square 45 minus 38 over 2. Okay, so 45 minus 38 over 2 is 26. So then tangent 26, we obtain the same value, which is 0.24, or 0.237. Okay? So that is for the KA. Okay? While for the KP, okay, if we doesn't want to use the equations for the KP, okay, actually the KP is equal to 1 over KA. Okay. Okay. So 1 over 0.24 is 4.17. Okay. Let's say we use the equations. Okay. 1 plus sine 38 over 1 minus sine 38. Okay. So then we obtain 4.20. Okay. Okay. Because if 1 minus 2.37, so then we obtain 4.21. Okay. But we have used 0.24, so then the value of the KP is 4.17. Okay. But for the soil number 2, KA is 1 minus sin 28 over 1 plus sin 28. Okay. Which is 0.36. Okay. Then the KP is 2.78. Okay. So then look on the calculations. Okay. So this is this is has been simplified. Okay, so if you look on my on the derivation, okay, so I explain, okay, how does the value obtained. Okay, okay, for the lateral stress determination, okay, so we need to calculate, okay, first at the initial value, okay, then we need to identify if there is a changes of the soil properties, okay, due to different type of material. So that is the first, or due to the existing of groundwater level. Okay. So for this case, okay, since there is a two type of soil, which is soil number 1 and soil number 2, okay. So then we need to determine, okay, what is the active active lateral pressure, okay, at depth of 6 meters. Okay. So it means that we should calculate for the initial at 6 meters and the last one at the end of the sheet pile layer. Okay. Okay, if there is a changes of the soil properties, okay, so we need to consider both of soil conditions. In that case, there is a area where we need to calculate for slightly above and slightly below. Okay. So that is why in this example, okay, so they have first calculations at 6 meters to represent the soil number 1 and another 6 meters to represent the soil number 2. Okay. If you refer to some of the textbook, okay, they explain this is called a slightly above and slightly below, because we have different value of C and Phi, okay, for this first soil layer and second soil layer. Okay. So then we look on the how the solution works. Okay. So I explain here, okay, slightly above and slightly below. Okay. So since there is a surcharge on the top of the soil, so then we need to consider the surcharge value as a vertical effective stress, then multiply with 0.24, then we obtain 12. Okay. So for slightly above, okay, so 15 plus 18 times 6, this is for the effective vertical stress. So for the lateral lateral stress is effective vertical stress times with the Ka value. Okay, so then we obtain 37.9. Okay, so this is how 37.9 is given. Okay. Then for slightly below, okay, the same effective vertical stress. Okay. Since the soil number 2, it has C and Phi, okay, So then we need to use the equations where it represents the C and phi value. Okay? So for the C and phi value, so then we use this equation. Actually, for the SWOT number one, we also can use this full equation. Okay, since C is 0, so we only rely on the first sub-equation. Okay? So 158 times 0.36 minus 2C square root KA. Okay. So then we obtain 44.8. So look on the example on here. So we obtain 44.9, which is on this on this solution we obtain 44.88. Okay. And then for at the depth of 9 meters, okay, obtain the effective vertical stress. Put the value times 0.36 minus 210 times square root 0.36. So the value is 55.9. So then for the passive part, okay, at 0, okay, so this is equal to 0. Okay. So at 1.5, which is we have two slightly above and slightly below value. So for the slightly above is the 18 times 1.5 times 4.17. But in this case, I put 4.20. So we obtain 113.4. Okay, this is 112.6. For the slightly below, okay, 108.4. In this case, 108.4. Okay. So then at the 4.5 meter, okay, the value is 193.5. Okay. Then we plot the distribution pressure diagram. Okay. So this is the distribution pressure diagram for the active. Okay. So at 6 meter, we have two. Okay, wait a minute.
Assalamualaikum.
Kejap, ada kelas. Sorry, I got a call from my son. Okay. So then, okay, so this is the distribution diagram for the active, while this is the distribution diagram for the passive. Okay. So this is a pressure. Okay, let's say if you want to determine what we call as the load. Okay.
Sir,
Yes, yes.
We cannot see the screen, sir.
Oh, okay, 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 okay. Oh, because okay, okay. This is the pressure. Okay, let's say if you want to get what we call as the load. Okay, so what should you do? You need to divide it into several areas. Okay, so you put the first area. Okay, please only use what we call it triangle or square or rectangular shape. Okay, so this is first area, second, third, and fourth. Okay. Okay, so then to get as a load, okay, so then get the area here of the first one, second, third, and fourth. Okay, why we need to use rectangular, square, or triangular shape? Because we want to determine the moment arm later on is much more easy if we consider a trapezium shape. Why we need to determine the moment arm? Later on, we need to identify where is the locations of the line of loads. Okay? I will later on share with you another example, a complete example uh, to determine the pressure, loads, and also the moment. Oh, sorry, the location of total thrust. They call it location of total thrust. Okay. So that is for the example number one. Okay. So this is for the passive part. Okay, we have two value at 1.5 meter depth. Okay, and also at 4.5, the value is 197.82. Okay, so then to get the area, okay, this will be the first one. Okay, then this will be the second, and this will be the third. Okay, so that is for the passive part. Okay. Any question before we move to the second example? Okay, if no, we go for the second example. Okay. Okay, this is second example. Without having any what we call as a groundwater. Okay. The question asks calculate the corresponding prop load F, okay, to stabilize the this retaining wall here. So the soil, the phi value is 30, gamma is 20, okay, and the height for the H is equal to 5, okay, and D is considered the embedded depth in the soil. Okay. Okay, so there is an explanation there. Okay, then I try to explain. Okay, for each what we call as the sentence. Okay, for example, it explains the vertical total stress at any point on either side of the wall is given by the unit weight of the soil multiplied by the depth below the appropriate soil surface. So stress is equal to gamma times H. Okay, so this is a vertical, as a vertical. Okay. So while for the effect, okay, the vertical effective stress is obtained by subtracting the pore water pressure, which in this case is zero because the soil is dry. So the explanations of the effective stress is total stress minus with the pore water pressure. Okay, but for this case there is no pore water pressure, so means that the effective stress is equal to the total stress. Okay. The horizontal effective stress at the depth of Z below either soil surface are Ka times effective stress vertical inactive behind the wall and Kp times effective stress in the passive zone in front of the wall. So then Ka and Kp are active and passive earth pressure coefficient. Operational wall are as defined in equation 7.3 7.4. Okay, because this I'm referring to another text. So I just put what is equation 7.3 and 7.4. So we may refer to this equation Ka and Kp. Okay. So then it follows that in this case both the vertical and horizontal effective stress increase linearly with depth of the wall shown in your slide. Okay, so this is 7.16, okay? And I also include in this um, solution. Okay? So this is what we call as the distribution diagram until to the end or to the toe of the retaining structure for the active, and this is for passive. This is what how the what we call the distributions. Sorry, the more circle plot, okay, for the active and also for the passive. Okay. Stress distribution are often either triangular. Okay, this is triangular. Either triangular, this really or depth formed with depth, or they also can be a square. Okay, so for the purpose of taking moments, okay, so this is discussion on the moment. The resultant force acts through the center of the pressure, which is at the geometric centroid of the shape, defining the stress distributions. Okay? So in the case of triangular stress distribution of overall depth, the center, this is for the triangular, right? The center of the pressure is a depth of 2d over 3 from the triangle. Okay? So this is the resultant of the diagram. And to get the then to get what well action So for the triangular shapes, it is a 2/3 from the height. If we put on the top, or if we refer on the top, so or it is 1/3 of the height if we are referring at the bottom. Usually we are referring at the bottom, okay, because we use the datum or the origin location based on the two locations or the two positions. Okay. And for the rectangular shape, okay, the resultant force is the area, and the line of action is half the height, and same use as the datum. Okay. Okay. So then we do the calculation to determine what is the force to stabilize, called as the wall. Okay. Okay. For the stress distribution shown in figure 7.16, considering a 1 meter length of the wall perpendicular to the plane of the paper, it taking about the give. So means that in this case, because in reality it is a three-dimensional geometry, okay, because we have discussed before that we use the plane string as approach, okay. So it means that the value of the load or stress is considered per meter run. Okay. So per meter run. For every 1 meter, so that is the load applied on the returning wall or to the soil. Okay. Okay. So now we try to guess, okay, what is the depth of the B? Okay, we want to get what is the depth of the B. Okay. So this is the first part, okay, for the active, but this is for the passive. Okay. Okay, in this case, the datum is considered at this, at the top, okay, or at the F. Okay. So if we consider this as the datum, then we use the 2/3, okay, for the triangular shape. If we consider the datum is at the bottom, then we use the 1/3. Okay. So for this case, the author used the S, the point as F as the datum. That is why H plus D times 2/3. Okay. While for the passive, it's plus 2D/3. This 2D/3. Okay. So, okay. So to get the D, solve this equation. So we obtain this equation, then we need to do a try and error to get what is the value of D. Okay. So you can use your calculator then try to play around, okay, what is the D value, okay? So based on the calculation, the D is approximately equal to 2. Okay, so the easy way we put 2, okay, as the D value. Okay, so that is for to determine. Then we use the D, okay, in order to determine the F value. Okay? So it means that this is the load. Okay, this is the load. Okay. So the load we obtain from the area here at active. Okay, but this is the load from the passive. Okay, also get the area of the triangle. Okay, then plus with the F. Okay, so it means that F and this part contribute to the stability of the cube. So from there we can get what is the F. Okay. So the next patience is on lower bound toxicity, okay, to estimate, okay, what is the lowest D, okay, that can be obtained, okay, means that the upper part is 2 meter. And what happened, what is the minimum for the D, okay, which is considered as the lower bound. The lower bound, okay, we assume that the based on the conditions to stabilize the soil, okay, so definitely the sigma H, okay, is greater than the Ke times gamma Z, okay. Okay. On the other side, the Kp should greater than the sigma H. Okay. So then the Kp times what we call as a delta Z minus H should greater than the active area. Okay. So therefore, it can what we provide a more stable conditions. Okay. So then we try to put Z on the left, okay, and the rest on the right. Okay. So later on, the Z is represent the D, okay, because Z minus H, okay, we obtain the D. Okay. So then D, okay, is 0.12 times H. Okay, put the H inside the equations, then we obtain D is equal to 0.625. Okay. Okay, so that is for the this example. So then H is if yeah, if H is equal to 5, so then we put the H value in the in our answer, then we get the D is equal to 0.625. Okay, so means that the range of the D, okay, is starting from 0.625 to 2 meter. Okay, okay, so that is for the example number 2. Okay, so this is a further explanation. Okay, to explain, okay, why it has two value T, okay, which is the minimum is 0.625 and the height, the maximum is 2 meter. Okay, for this example. Okay. Okay. Okay, before we move to the next discussion, okay, let me find another example, okay, and we determine the what we call as the force and the load and also the actions, line of actions. Okay, so I need to open to another example. Let's start this. Okay, I share to your WhatsApp. And after this example, we take a break. Yeah, I'll share to your group. That is the example. Open the example. Okay, so this is the example. To we try to do one by one. Okay, for the first example is on the what we call at rest. Okay, figure Q11 show a rigid wall. Okay, can you see the second? So this is the first example. So we need to stop first in a second. So this is figure Q1, show a rigid retaining wall of a proposed basement of a shopping mall. Assuming the wall is raised by beam so that no yielding is allowed. Calculate the total thrust and locate the line of actions. So we need to determine what we call as the total load. So locate the line of actions. In this case, we need to use the equation of at rest. So no yielding is allowed. So it means that there is no movement of the wall. So the wall is stable. So in that case, we consider it is in rest conditions. So the equation for the at rest is 1 minus sine phi. Okay. So as I mentioned, okay, first we need to draw the distribution determine the and the initial. Okay. If the case of the soil properties, so that will be the set. That will be the next depth, and the last one should be the stress at the tip of the retaining wall, or the toe of the tip of the or the end of the retaining wall. Okay. So this is the soil properties that is overburden 20 kilometer per meter square. Okay. The first soil layer is 4 meter and followed by 3 meter. The soil properties are shown in the figure Q11, okay, for the first and second layer of soil. Okay. So the first step is to determine the phi and followed by the K naught. Okay. Then we start to determine at the initial value, okay, initial depth, which is Z is equal to 0. Okay, the given effective vertical stress due to the surcharge is 20, then multiply with the K naught at the depth of 4 meter. Okay, in this elevation, a change in the strength parameter P is observed. Therefore, two different lateral stress will be considered, slightly above and slightly below this level. Note that the effective vertical stress at this level is unchanged. Okay, so means that we still can't use the stress at 4 meter depth. So 20 plus 17 times 4, the effective vertical stress is 88. So we use the 88 for the slightly above and slightly below. So then for the slightly above is 88 times 0.5. Okay. While for slightly below is 88 times 0.658. So at the depth of 7 meter, so then we obtain 94.41 for the lateral stress at rest. Okay. Then we plot the distribution diagram. Okay. So we have 10 at the initial pressure, okay, followed by 44 and 57.9 at 4 meter, and the last one is 95.41. Okay. So to get the total resultant thrust, so then we need to determine the area. 1 plus A2 plus A3 plus A4. Okay. So as I mentioned to you before, we need to consider only rectangular, square, and also triangular shape. Okay. 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 The last part is to determine, okay, the line of actions. Okay. So P naught is the line of action for the all location or for the all loops acting on the wall. Okay. So then we start to calculate for the P1, P2, P3, and P4. Okay, how to get the P naught? So the P naught is equal to Y naught, Y average. Okay. So P naught is equal, is time Y average is equal to P1 times Y1 plus P2 times Y2. And follow until times Y4. Okay. So from there, what is the Y average when all the value of P1 plus P2 times Y2 until P4 times Y4 over P naughts. Okay. Then we can get what we call as the Y average. So the P naughts here, okay, 337.97. Okay. So then the locations of the resultant thrust is located at 2.4 meter above the base of the wall. Okay. 2.4 from the base of the wall. Okay. If we use B as the datum, so means that we use 1/3 for the triangular and half for the rectangular shape. Okay, this is for the moment. Okay. The one that we have discussed before, they put or they consider at the top. Okay. So that's why they use the 2/3. Okay, any question? For the first example, before we go for the second.
Sir.
Yes, Martin.
So, regardless if we use A as our datum, right? The surface, we will still have the same answer, right? Just that the value it will be the value of height will be different lah for each
Yes,
for
that's
each
it.
area. Yeah.
Uh,
Okay. All right.
Usually for retaining wall, okay, we use what we call as the toe or the tip of the retaining wall as the datum. Okay. However, for the slope, the slope, usually we use the top, okay, as the datum. So then for the slope, we use 2/3, and for the 2/3 for the moment arm, okay, and for the retaining or horizontal lateral stress, usually we use 1/3 because we refer to the bottom of the retaining wall. Okay. But there will be no problems, okay? But we need to consistent of datum value or locations. Okay? All right.
Okay, sir. Thank you.
Okay. So now we look on the example number 2. For example number 2, okay, a 5-meter high retaining structure shown in figure Q1(2) was designed to support backfill with a perched water table. Okay, so there is a water table there. Based on the Rankine theory, determine the total lateral thrust due to the soil and the water acting on the structure if the wall is allowed to move to the left sufficiently. Okay, so in this case, they mentioned that wall allowed to move to the left. Okay, so means that if the it is active conditions. Okay, so then we need to use the active equations to solve these problems. Okay, the total lateral thrust, so means that the loads, so we need to plot for the distribution pressure diagrams. Okay. Okay, so the same procedure, okay, but with the use of the uh, active equations. Okay, then this is what equation, a general equation for typical soil. Okay. Okay. So that get the KA for the active. Okay. So as I mentioned, start first with the initial, continue with any changes of the soil, and then at the end of the toe. Okay. So we have 3 locations, okay, that we need to consider. Okay, uh, Z is to 0. Okay, okay, for KA, the same value, the KA is equal to 0.1. Clear, the KA is equal to 1 because the phi is equal to 0. Okay, so then start first with the top of the soil. Okay, let's say if there is no surcharge, okay, so please do not jump to the conclusion that your effective horizontal stress also becomes zero. Okay, okay, because the equation depends on the soil properties. Okay, if there is a C value, so then your initial horizontal effective stress will give a negative value. Okay, because if the sigma V is zero, so this will be zero. But if you have a C value, so your initial at the initial height, your effective horizontal stress will become negative. Okay, later on we will look on that example. Okay, so please be careful. Okay, yeah, if there is a surcharge, definitely the effective vertical stress has a value. Okay, if there is no surcharge, the effective vertical stress is equal to zero, then please do not put your effective horizontal stress also as zero, because you need to include the C in your equations. Let's say if the C is zero, so means that you have confirmed that your horizontal effective stress also zero. Okay. Okay. For this case, the C is zero, so means that your effective horizontal stress also zero. Okay, U is the pore water pressure. So since it doesn't have any pore water pressure at the top, so U is equal to zero. Okay, so then for the Z is equal to 2 meter. Okay, so 17.6 times 2. Okay. Since there are no changes in soil parameters C and P, we need to consider the active pressure at points slightly above and slightly below this 2 meter level. Okay. So no changes. There are changes. Sorry, I mentioned before no. So there is the changes. Then for slightly above, okay, um, the value is 11.72, okay, and slightly below the value is negative 24.8, okay, because when we include the C value, okay, it is more greater than the first equations, okay, so then it showed negative 24.8. Okay. So at the depth of 5, okay, so then we calculate for the effective vertical stress and then get what we call as the horizontal effective stress. Okay. So we need to differentiate between the hydrostatic pressure and also the what we call as uh, the the effective horizontal pressure. Okay, so that's why we use the term of effective, because the water doesn't experience any shearing. Okay, the shearing only experienced by the soil. So that's why we use the effective stress approach. Okay, so then when we consider the pore water pressure, okay, in this case, the author used the value of 10 to represent the unit weight of water. Okay, from our previous example, we use 9.8 to represent the unit weight of water. Okay. Okay. In order to calculate for the what we call as for the uh, active total thrust, okay, or active pressure, we only consider the positive pressure, okay, because in this diagram, okay, we have a negative force and also a positive force, because the expansions that push the wall to the left side is only contributed by the positive pressure. Okay. So then we need to determine, okay, what is the value of y, okay, or the heights on the positive sides. Okay. So how to get the value of y? We need to use a similar triangle approach. Okay, what does it mean with seeing a similar triangle? Okay. So it means that the ratio between the left and the right is equal. Okay. So it means that 24.8 over 3 minus y is equal to 4 over y. Okay. Okay. So then try to solve the problem. Then we obtain y is equal to 0.417. Okay. when we when we calculate for the total thrust, okay, so we also need to consider the hydrostatic pressure as well, because hydrostatic pressure also the wall. Okay. So then we have A1 plus A2 plus AU. Okay. So the value of the P is equal to 57.6. Okay. So that is for the example number 4. Any question? Is there any question? Okay. Clear, eh? Okay. All right. Okay, I guess better for us to take a break, okay, before we continue further for number 3 and example number 4. So we meet at 10. Okay? So please get your breakfast, then we continue at 10:10. On the recording. So see